All right, everyone, this is the lecture that I am doing to replace our normal Friday lecture that I would normally be giving on March the 27th because I'm going to be in San Diego. And so what we're going to talk about is a little deviation from what we've been doing, but it works well because I'm not going to get back until late Monday night. And so we won't have to worry about a lot of technetium. You don't have to do any prep for the lab this week. But what we're going to talk about is I-131 instrumentation, and specifically the two types of things that are related to instrumentation related to I-131, which would be air monitoring and thyroid bioassay. So we're going to talk a little bit about air monitoring. We're not actually going to do that in lab, but I am, as part of the lab assignment, you are going to actually have to do your own thyroid bioassay. And we'll talk about why these things are important as we kind of move through this PowerPoint presentation. So objectives, we're going to talk about hazards of radioactive iodine. We didn't spend a ton of time on radioactive iodine, so I'll touch on a few of those things here. We'll talk a little bit about why we do air monitoring and what the requirements are for doing air monitoring. I have on here review the calculations. Since we're not going to spend a lot of time with this, we'll talk a little bit about how you would do it and what kind of information you need, but I'm not going to make you do any type of calculations. Pretty much in a pharmacy, they have this set up so that it's a computer-based program, and so most pharmacists don't have to spend a lot of time doing any kind of calculations specific to this test, but we will at least kind of talk about what the requirements are and how that relates to what we actually do during the test. The last part of this is going to talk about performing a thyroid bioassay. We'll talk about bioassay, what it is, and basically then we'll go over this step by step, because when you actually come to lab, this is what you will be doing. Setting up a machine and going through the whole process of counting your thyroid gland to determine if you have any radioactive iodine in your gland, and as you can imagine, you probably will not, since we haven't worked with any radioactive iodine in lab to this point. And then last, we'll talk about one of the few places where statistics actually plays a role in the documentation of a test, and that is for thyroid bioassay especially. We're going to do some tests that are statistical in nature to try to determine if the data that you are collecting is as accurate as it possibly can be. So let's start off just by doing a quick little discussion about iodine. Iodine is one of these agents that we use fairly frequently in nuclear pharmacy. We actually have two versions of it, I-123, which is a gamma-emitting isotope with a short half-life of about 13 hours. And basically, when we use I-123, we're usually using that diagnostically, meaning we are trying to determine the function of the thyroid gland. Quite often you'll hear this described as a thyroid uptake or a thyroid uptake in scan. And basically we're just looking to see how well your thyroid is functioning. Usually it's in patients who are hyperthyroid or who we suspect hyperthyroidism, so that we can go in and actually determine the root cause of the hyperthyroid condition, and also to prepare for therapy if we choose to do radioactive iodine therapy. I-131 sodium iodide is the therapeutic agent that we use. While it can also be used diagnostically, in some pharmacies we actually, instead of using I-123, we use I-131 for the diagnostic component, the thyroid uptake and scan. I-131 has an 8-day half-life and a 364 keV gamma, which basically makes it a little challenging to actually get good images, because that very high energy gamma is very difficult to actually image. But when we are doing an uptake study, we can get just as good information from I-131 as we do from I-123. Probably the thing that you're going to see I-131 used more frequently for is for the therapeutic applications to actually treat hyperthyroidism or to treat thyroid cancer. And so in patients who have an overactive thyroid gland, we can give radioactive iodine. It's going to get taken up in the gland just like regular iodine does. You make thyroid hormones with that iodine, and what ends up happening is it gets trapped in the thyroid gland, and the beta radiation that is characteristic from I-131 basically is going to ablate some of the thyroid cells. And the plan with hyperthyroidism is to try to get rid of some of the cells, but not all of the cells, because you'd like to still have a normally functioning thyroid gland if possible. So we basically are just trying to knock some of it out so that we get back to a euthyroid condition. The other use of this is when we have a patient who has thyroid cancer. Most of the time, we will treat thyroid cancer by physically removing the gland. The patient will have surgery to have it removed, but most patients will have some amount of residual thyroid tissue after that removal, and or they will have metastatic disease that has spread outside of the thyroid itself. And so we can use radioactive iodine as a whole body treatment for those kind of conditions. The difference obviously is in hyperthyroidism, since we don't want to get rid of all the cells, we give a smaller dose, and in thyroid cancer we want to try to wipe everything out that we possibly can. The doses for those are going to be a whole lot higher. So as I mentioned, I-131 is a beta emitter, which makes it ideal for therapy applications. It also gives off a gamma, although as we mentioned, it was a very high energy gamma, but that does allow it to be imaged, which is kind of unique. Most betas can't be imaged because the betas don't travel that far. In a human tissue, the I-131 betas travel about 1 millimeter. So basically, if you had a pure beta emitter, you wouldn't be able to do any type of imaging to determine if it localized anywhere in particular. So the gamma that is associated with I-131 is actually going to be helpful, because after we give the dose, we can put the patient under the camera and try to figure out what's going on, where it went, if there were areas that didn't get treated sufficiently, things like that. So I-131 is pretty straightforward when we talk about it from a pharmacy application, except there's really one major thing that we have to think about. And quite honestly, you think about it with I-123 as well, although because it's a gamma emitter, it's not as worrisome. But iodine has a tendency to volatilize. And so because we have that condition, if you inhale this as part of the volatile component, you actually will see that the iodine would get into your system, get into your thyroid gland, get in and actually ablate some of the tissues in your glands. So obviously we know that you could stick yourself with something, or you could ingest something. We talk a lot about how we try to prevent those things from happening, but volatile iodine is a little more challenging because you can't really see it. We don't know how much is actually there. And so that is a risk whenever you handle any type of iodine, but iodine 131 most particularly for practicing nuclear pharmacists. But this risk, while it is the greatest risk, or one of the greatest risks, it's still a pretty minimal risk. But the reason why is because we do a pretty good job of teaching folks how to handle it properly, and we have several pieces of equipment and ways of monitoring that we use to try to make sure that the people who are handling it safely. So as I said, the biggest problem with this is iodine is volatile. And so basically, even in capsule form, iodine comes either as capsules or as a solution. And even in capsule form, you'll see some volatile iodine that's actually released. And when you open up the container, out comes a potential puff of volatile iodine. So we need to think about that every time we handle a container of iodine. The way that we do this in a nuclear pharmacy is most of the time focused on the equipment that we're going to use. So if you are actually going to be having I-131 in your facility, we don't just leave it out on a shelf or on a tabletop. It's stored in a fume hood, and that fume hood is going to be vented to the outside. And so basically any volatile iodine that actually is created in that process is going to be vented out. It's going to go through some filters to try to trap the iodine, the actual radioactive component of the iodine, so that we're actually releasing things into the outside environment that are no longer radioactive. When we actually manipulate it, and as I said, we have liquids, sometimes we have capsules. We also can make our own capsules, which we take liquid and just put it into capsule form. And if we do any of that kind of manipulation, we actually will do that in something called a glove box. There's a couple reasons for that. Number one, because we can kind of isolate it. That's probably going to be the most likely place where you'll spill something. So it's easier to clean up than in the area where you're storing all of your stuff. But also because the fume hood, we have, as I mentioned, we have filters in there that trap the radioactivity. It's a little more challenging to change the filters in a fume hood than it is to change them in a glove box. So we do most of our manipulations, compounding, potential spilling in the glove box. If we do spill, we have charcoal filters that we can use to help trap that radioactive iodine, but it's very easy to change those out and clean up the mess once it's done. The other thing that we can do is try to minimize volatility as much as possible. If you actually see the iodine that we get from a manufacturer, they add a variety of stabilizers to the formulation to try to keep the pH more on the basic side. And so essentially by doing that, it does help cut down on the volatility. Some people add additional stabilizer, whether or not that's absolutely necessary. It's kind of, some people it's just a normal practice for them, other people don't do it. The other thing that you'll see a lot of times is people will actually, when they first get a vial of radioactive iodine, especially the liquid kind, will take a 10 cc syringe that's been filled with charcoal, and we'll talk about charcoal here in a second, but it's a really good trapping material for radioactive iodine. And we'll take this 10 cc syringe, we'll stick the needle into the vial, and we'll just basically pull back air, just like I have you do after you make a kit. But what will happen is it's going to suck the air, the air inside of the vial, the headspace, which is where you're going to have a lot of volatile iodine. It gets sucked into the syringe, the iodine gets stuck in the charcoal, and then we can basically just throw that away. And so a lot of times you'll see people doing that when they first get a vial of iodine, because there's been a delay between manufacturing and receipt in the pharmacy. And so the assumption is that's probably where you're going to see a lot of your volatility occurring. And so the headspace would basically have a lot of volatile iodine in it. So the equipment itself is what we consider to be a major protection for the workers. So you are going to be handling this if you work in a nuclear pharmacy. And your goal is obviously to maintain ALARA principles, or to keep your radiation exposure as low as possible. And so if we can figure out how to work with this particular drug and work with it safely and effectively, your radiation exposure can still be very, very low. But the way that we make it, the fume hood, the glove box, the equipment we're using, are all designed to help keep the worker safe. The other thing that we'll do in relationship to these equipment are monitoring. So you don't just put a piece of equipment in and think it's going to work. We have to actually prove that it's working. And so we have two types of tests that we actually are going to do, and that's what we're doing in lab this week, or what we're talking about in lab this week. And the first one is frequent monitoring of the equipment itself to make sure that it's working. And we do that by doing something called air monitoring that we're going to talk about first. The other thing is we're going to actually test the user. So in our case, it's a pharmacist. We can do it sometimes with different members of the staff. Some people do it with their drivers. It really just kind of depends. But we can actually go through, and since any radioactive iodine exposure that you're going to get is going to end up in your thyroid gland, we're going to test your thyroid gland by way of bioassay to try to figure out if you were taking any iodine in. And if we find out that you are, then we can do things to try to adjust your technique, or double check the equipment, or try to figure out where the source of the radioactive iodine inhalation actually occurred. So as I mentioned, charcoal is the trapping material that we're actually going to use. So whenever I talk about a filter, whether it be in the glove box, the fume hood, things like that, charcoal is going to trap radioactive iodine. So if we have any iodine in the air, if we pass the air through a charcoal filter, you should be able to trap most of it before it actually gets either vented to the outside environment, or ends up in the room where you're actually going to be potentially breathing it. So as I mentioned, when we talk about this, where do you put the volatile iodine? Whenever you do radioactive iodine in your pharmacy, there are significant regulatory requirements to make sure that all of this system works well. And so we got to do something with volatile iodine, and you can't just pump it back into the environment. So what we actually end up doing is we pump all of the air that's going through this glove box and fume hood out into the external environment. So most of the time you'll have a fume hood that will actually have a stack that will go out through the roof or through the wall, and the air is actually going to be vented out into the outside environment, which is non-restricted, which basically means you can't just throw radioactivity out there. So basically we will use the charcoal filters to try to trap as much of the iodine as we possibly can, and then the hopefully clean air is going to vent out into the outside environment. Now, while charcoal is a great trapping material, it has limitations. And the limitation is once it binds iodine, there are a limited number of binding sites where it can actually grab on and hold on to the iodine. So if you keep passing this stuff through the charcoal filters, eventually the charcoal filters are going to get full. And so if you can't stop it, the iodine goes farther and farther and farther and farther. And so air monitoring is one of the main things that we do when we talk about air monitoring is we are going to be checking the air that's going outside of our pharmacy, the stuff that's getting vented out. And what we're constantly trying to do is to make sure that the amount of radioactive iodine that's slipping through is below a incredibly small limit that has actually been set by the NRC. And so when we say air monitoring, that's what we'll do. We also do air monitoring to just do a general check of the environment. So we can do air monitoring all over in the pharmacy. And it depends on where you're doing the monitoring, but basically we just suck some of the room air through a charcoal filter and then try to determine if there's any iodine present in the room air that you're actually breathing. Now, the picture I have here is just a typical fume hood. You can see that it's got a sash, and basically this fume hood vents out to the outside environment. You can't really see the stack going out, but it actually has an inward pressure or a negative pressure. So airflow from the outside room is being sucked in through the sash. That prevents anything that is volatile that is created inside of that fume hood from leaking back out. A fume hood in a typical nuclear pharmacy is going to run constantly because we have the radioactive iodine. We also keep xenon gas and other types of radioactive material in there. We also keep a lot of waste. Kind of up in that area where the radioactive sticker is up on the top, that is the area where your charcoal filters actually are. And so the air comes in, it goes up through the ceiling or the roof of the fume hood, and then it's going to start passing through the charcoal filters, several charcoal filters, before it's actually vented to the outside. This is a typical glove box. The glove box is where we actually do most of our open manipulations. You can see that kind of blue cube on the top. That's actually where we keep the charcoal filters. And since there's a possibility that you're going to be handling large quantities of iodine in this area, usually that box is going to have 2, 3, 4 charcoal filters. So if the first one doesn't get it, the second one hopefully will, then the third one. The tube that's coming out the top there actually ties into the fume hood. So the air that's in there is going to get vented out just like the air in the fume hood. And so again, because we have the larger quantities of material that we're actually opening and manipulating, this is where we need to be really careful about trying to trap as much iodine as we possibly can. And so that's going to get shunted out into the outside environment. This is just a little schematic. You can ignore it if you'd like. But basically, when we do air monitoring, like I said, we're going to determine how much iodine we're exposing ourselves to if we're practitioners, which is what we sometimes call the occupational exposure. The other thing that you'll sometimes hear it called is the restricted exposure because it's sampling the air in the restricted area. We also will be looking at how much we release into the external environment, or what we call effluent. And if you remember back to our regulatory course, one of the things is we talk about wastes and how we handle wastes and things like that. We do have to worry about how much of this stuff we actually are releasing to the external environment, how much of the radioactive material, whether that be through airflow like this, or putting things down the sanitary sewage system, running it down the sink, things like that. Those are what we consider to be effluents. And so in this particular case, we're going to be evaluating the effluent, the air that's going out of our facility. Now, I mentioned earlier the limits to this are incredibly small. Obviously, we're not going to be perfect. We can't trap everything. But we also are very cognizant of the people who are outside of our pharmacy. As I mention all the time, John Q. Public does not sign on to work with or get exposed to radioactive materials. And so if we're venting stuff outside, we need to make sure that it is as clean as we possibly can. So if you'll notice for this, the effluent, or the stuff that's going out the stack, or the stuff that's going into the non-restricted area, is 2 times 10 to the negative 10th microcurie of iodine per milliliter of air that went through the system. The occupational, or the one that's the restricted area, is 2 times 10 to the negative 8th microcuries per mil of air. So both of those numbers are incredibly small. So how do we do this? Well, basically what we need to do is do an air sample. So we have filters that we actually place near the pharmacist compounding area most of the time when we look at the restricted filter. And so it's usually very close to the pharmacist's face because you're trying to sample the air that the pharmacist would actually be breathing while they're doing the manipulations. And so literally it is just a charcoal filled, either a round disc shaped charcoal or a long or skinny kind of charcoal filter that fits inside of a tube. And what we'll do is when we start the test, we'll put that in place, and then we will actually pull air across that filter at the same rate that we use to run the pump of the entire system. And then basically over some period of time, usually a week, we will just collect as much iodine as is present in that area. And then basically at the end of about a week, we'll go through and we'll try to determine how many microcuries of iodine are on that filter. If we have a pump that's running at a constant volume and then basically run it for X period of time, you can easily figure out how many milliliters of air went over that filter. And basically we just take the microcuries of iodine that are on the filter and we divide it by the number of milliliters that have gone over the filter, or how much went through to potentially deposit that much iodine. And then essentially that is what our limit is, microcuries of iodine per milliliter of air. So essentially this restricted filter really checks the function of the glove box, because that's really where we're doing most of our manipulations. And since it's usually right by where the pharmacist is working, where their arms are, it's a great way of seeing if you actually have stuff that's shunting back out. And so you can kind of see in my little schematic there, the glove box, the two armholes, those two circles are basically where your arms would be. So your face was kind of standing right up there. When you stand up is right there next to that restricted air filter. And so that's the air that we actually choose to evaluate. The unrestricted filter is basically put in place between the last charcoal filter in the fume hood and the vent to go outside. So technically we should have completely cleaned the air, and then we're getting ready to shove it outside. And so we want to be able to evaluate if that is really clean. Now, most of us are not keen on trying to climb up to the roof and take samples, so what you'll see in a lot of facilities is we'll do a bypass, where basically we have a tube that comes out at that point, and we'll actually bypass down to the level where you're going to be standing. And then we put a charcoal filter in the line, and then basically run the tube back up and outside. And so you basically just vent some fraction of that air over that charcoal filter. And then we do exactly the same thing. How much is on the filter in terms of iodine? We figure out how much air went through the system over the course of our testing period, and then basically we can calculate our effluent level. So technically, since this is going to the outside world, it should be uncontaminated. And so you can see kind of off to the left-hand side there, I drew a schematic where we have the unrestricted air filter. So again, I'm not going to have you do this, but just to kind of give you a couple of things. It's really not a complicated thing to do. You do need to have a pump that's running, and it should be running constantly with a set airflow. And so I will know that it's got 10,000 mils per minute of air going through, or something along those lines. And so basically that should be consistent. If I know how long the pump has been running, which is basically last week's test to this week's test, then basically we can calculate the time, and then by multiplying the airflow times the length of time, you'll get the total number of milliliters that have actually gone through the system or have potentially deposited iodine into your charcoal filters. The next thing on this list, a barium standard, or you can also use an I-131 standard, although most people prefer barium because barium has a 10-year half-life and we don't have to keep buying new standards to do comparisons. We're going to actually use the barium standard to determine the efficiency of our machine, or what fraction of what is there the machine is actually able to see. Just like we talked about when we talked about the single channel analyzer, we did some efficiency calculations. So we have to do the same thing for this. The problem, a couple of things with that, the barium is not iodine, so there's a slight difference between the efficiency of the machine for barium and the efficiency of the machine for iodine. But probably the other major concern that we have is if we test this once a week, I-131 has an 8-day half-life. So basically, if you deposited all of your radioactivity on day 1, but you don't test till day 7, some of that radioactivity is going to decay away. So you'll see that all of the calculations for this have something called a barium or a I-131 photon yield factor. And basically what that is, it's a correction factor. And it corrects for the slight differences between I-131 and barium in terms of efficiency, but more importantly, it's going to kind of bump up our calculated value to make sure that we compensate for any radioactive decay that actually occurred during the survey period. And so you're going to see that your barium or iodine photon yield factor is always some number greater than 1. So basically we're going to take that barium standard and we're going to count it for a minute. And again, when we talked about efficiency that you did when we did the single channel analyzer lab, basically the 1 minute count of a known standard, something with a known amount of activity, that is basically what our machine is able to see. And then what we're going to do is we're going to take the activity of the barium standard and we're going to calculate an efficiency based on what the machine saw versus what it should have seen if it would have been able to see 100% of the material that was in there. Because you're going to correct all of your counts whenever you count this. If your efficiency of your machine is only 20%, then when you count your samples, you're only seeing 20% of what's really there. So we need to make sure that we correct for that when we actually do these calculations. Just as an FYI, I-131 and barium both have a fairly low efficiency. Usually it runs somewhere between 10 and 30%, and that's because of the higher energy, the 364 keV gamma. Our machines just don't stop it as well as they stop 140 keV photon. And so whereas a single channel analyzer might be able to be 90% efficient in reading technetium, it's only about 20-30% efficient in reading I-131. When you get ready to actually, we can do that very quickly. You count the standard, you have a calculated activity of that standard, you figure out your efficiency, and then pretty much you're good to go after that. We'll do a background reading, then you'll take your restricted filter, you'll go get it out of your holder and basically bring it over and you'll count it for a minute. Usually we'll count several samples, 2 or 3 samples, to try to even out the randomness of radioactivity. But then basically we count that filter. We now have something in counts per minute. Since you know the efficiency of your machine, you can convert that to disintegrations per minute using the efficiency equals counts over disintegrations formula. And then once you have it in disintegrations per minute, you can then convert into microcuries. So, and if, again, we want to know how many microcuries of iodine are on our filter, that's how we're going to do that. And we would count both the restricted filter and the non-restricted filter. Once you have those values, then basically you just take the microcuries of iodine that you calculated on your filter, and again, corrected for efficiency, and you're going to divide it by the total number of milliliters that actually went through your system, and you now have your bioassay level. Or your air monitoring level, sorry. And so basically we compare that level to the limits and we see if we're within specs. So like I said, that you're not going to do this. It's just kind of a FYI. This is one of the things that we do. Some people get a little iffy about doing radioactive iodine. If you know what you're doing and you know how your equipment is working, there is absolutely nothing to worry about in terms of handling radioactive iodine. But it is good to know the kind of procedures and processes that we put into place. As I mentioned before, iodine is a huge regulatory issue in nuclear pharmacies. And as I said, iodine is volatile, whether it's in capsule or liquid form. Now, some pharmacies are a little bit more leery of doing I-131. So some pharmacies just basically do what we call a middleman type of process. If a customer wants a dose, they'll order it from the pharmacy. The pharmacy will call a manufacturer, place an order. The manufacturer ships it to the pharmacy, and then the pharmacy ships it to the customer. And that's fine. There's nothing wrong with that. It takes a little longer. Obviously, we have to wait for shipping times and things like that. But in the pharmacy, we never actually open up the container. It's just like giving a patient a sealed container of 100 capsules. There's no need for us to open it because it's sealed from the manufacturer. So in this case, we never actually open the iodine. We just are the pass-through people. And in that case, then the chance of your volatile iodine exposure is pretty low because you never actually open the container. So if that's how pharmacies choose to do this, then usually the air monitoring requirement is pretty low. But you will also see that some pharmacies will do something we call custom compound I-131. And what they'll do is they'll buy a large vial of stock I-131 solution and they'll subdivide it into individual patient doses when they actually get an order. And they can do that either as capsules, where they draw up the liquid and then squirt them into capsules that are going to be administered to the patient, or they'll just give them a straight up solution, draw it out of the stock vial, squirt it into an evac vial, and then send it off for the patient to actually drink. They'll drink it through a straw type of apparatus when they actually get it for administration. Obviously, in this case, not only are you compounding or you opening the vial, you're manipulating the vial. And so there's a much greater risk of volatility and a much greater chance that you potentially can do something that's going to affect yourself. And so if that's what you do from a custom compounding, we tend to be a little bit more concerned with the regulatory aspects of that. And so you may see that some pharmacies will have only the pharmacists do bioassay and air monitoring. We'll see that some pharmacies will only do air monitoring in the iodine room. They won't do it outside. I mean, it really just depends on what the situation is in order to kind of set up what your regulatory requirements are. So you can go to a bunch of different pharmacies and see a bunch of different things all related to this particular topic. Now, the thing that we're going to do this week in lab is bioassay. And we do this because, number one, you can be a little bit more active with it, but also because it's going to work on your skills with your single channel analyzer. Again, we're going to work on setting up the single channel analyzer, making sure the single channel analyzer is working correctly, calculating efficiencies, and then hopefully calculating your bioassay. But just as a quick kind of review of bioassay, when we talked about regulatory stuff about occupational radiation exposure. And if you remember, you normally wear a film badge on your jacket, which basically monitors your occupational exposure. The occupational exposure right now for the US is 5 rem per year. And most of us always think, oh, that's external because we wear a badge, and that's true. But it also includes anything that you ingest in your body in the course of your occupation. So, if you went out and got a cardiac study because you needed to have a cardiac study, we can't count that radiation exposure towards your occupational exposure because you didn't get the exposure as part of your work. So internal, unfortunately, is a little bit more difficult to monitor. And this is why we spend a lot of time telling you you can't eat in a nuclear pharmacy because you can ingest things. We want to be careful about sticking yourself. Technically, we should figure out how much radiation got into your stick when you actually stuck yourself with a needle, and you should calculate how that impacts your internal dose. And then obviously in this case, if you ingest volatile iodine as part of your workday, then basically whatever you get to your thyroid gland should also be calculated. Now, bioassay itself, by definition, is the determination of kind, quantity, or location, in our case, of radioactive material in the human body. And we either do that directly, or what we call in vivo measurements, or by analysis of materials excreted or removed from the body. And that's what we call in vitro. When it comes to radioactive iodine, if you take it in, it's going to go to your thyroid gland, some percentage of it, and the rest of it's going to get excreted, usually in the urine, most of it in the urine, although sweat, tears, saliva, all of those liquids will also have some amount of radioactive iodine in it. So we could actually determine your iodine intake by collecting your urine and trying to figure out how much iodine was there. And if we can figure out what fraction of what was taken in is excreted in the urine, then we should be able to, by definition, figure out how much ends up in your thyroid gland. You can imagine that's messy, it's awful, nobody wants to do it. So what we do is we're going to do the direct measurement. And the direct measurement, obviously the easiest way to do direct measurement would be to take your thyroid gland out and actually evaluate it. But since that's not physically possible, we have to use our equipment and do some manipulations in order to get a measurement of how much iodine is in your gland. And that's exactly what we do when we do bioassays. We're going to try to figure out how much iodine is in your thyroid gland, and then we will relate that back to your actual occupational exposure. And if you have occupational exposure, then it has to go into your whole body record. So the other nice thing about bioassay, though, it's a great way of identifying technique. New people tend to have slightly higher bioassays or are closer to the limits or to to having recordable values than people who've done it for a while. But if you have a huge spill and you're trying to clean it up and you have some issues with that, even the best pharmacist is going to get some level of radiation exposure from the radioactive iodine. So basically, the other thing that this does is it tells us if the equipment is functioning appropriately. Obviously, we test the equipment once a week, but what happens if it broke on day number 2? Then, you're going to go 5 days before, 6 days before you actually identify if the equipment is leaking radioactive iodine. So by doing bioassay at routine levels, we actually will see if there's a trend where our staff is starting to get more and more iodine in their thyroid gland. So essentially, bioassay works very similar to air monitoring. So we are going to do this using the radiation detected methods that we have available in the pharmacy, which for us is going to be a single channel analyzer. Now, I know this is a terrible picture, but this is actually the same thing that we do in a patient who we are going to send I-123 and try to do a thyroid uptake study. In a thyroid uptake study, we actually intentionally give the patient iodine. It gets into their body, it gets absorbed from the stomach, it goes to the thyroid gland, and then we count the thyroid gland and try to figure out what fraction of the dose that was administered ended up in the thyroid gland. And so, like a normal thyroid uptake for a patient in this part of the country is between 10 and 30%. So basically, between 10 and 30% of the dose we administer to you ends up in the thyroid gland. If you're hyperthyroid, that number goes up. So if we have a patient that has a 68% uptake, then they're taking up a whole lot more iodine than the normal folks. And so this is basically what the patient will do. They'll come in, they'll take the capsule, they'll go home, they'll come back 24 hours later, they'll sit in front of that probe, which is essentially a scintillation probe or a single or a same kind of detector that we have in a single channel analyzer. And we basically just count the photons coming out of this patient's neck. Now, obviously, the photons, we're only looking at the photons that come in one direction. So as you can imagine, we need to do some geometry correction to make sure that we calculate the efficiency and figure out just exactly how much iodine is actually in the gland. So we're going to do something very similar, but as you can see here, we don't use a piece of equipment that's nearly that fancy. You're going to use the same equipment that you use to count your wipe samples and all of that kind of stuff every week in the pharmacy. And it works fine as long as you make sure you set up your equipment correctly. Now, the NRC requires, and by requires it means you must do, a bioassay if you work in a 3-month period, you handle open unsealed quantities of radioactive iodine in excess of 1 millicurie on the open bench, 10 millicuries in a fume hood, or 100 millicuries in a glove box. Now, the pharmacy I came from before I came here to Purdue, we would routinely do 3 or 4 curies of iodine a week. And so, obviously we exceeded this limit. We'd have in a glove box, we'd do 3 or 4 curies. So we basically far exceeded this requirement to do bioassay. And so our choice was we did bioassay twice a week. And basically that was, the hope was is that if with several pharmacists staggered out over several days, we would hopefully see a trend in increasing thyroid numbers sooner rather than later. But basically the NRC requires you to do it, but they also let you establish your own guidelines based on how much iodine you're using and what's actually coming in and out of your pharmacy. Like I said, if you handle mostly unsealed quantities, then bioassay also becomes a less frequent necessity in your facility because you don't necessarily meet this particular requirement. Now, the NRC also recommends that you do bioassay if you handle 10% of those amounts. It's really not a hard test. It doesn't take long. And again, our goal is always to find a problem before it becomes a problem. And so most pharmacies will still have a routine bioassay procedure in place. In my last pharmacy, we did it even if I opened and never made iodine all week. I still did thyroid bioassay every week just to kind of be part of the data collection point, so we could see if there were any trends that developed. The one thing with bioassay that you have to be careful with, I spilled radioactive iodine on myself at one point in time, a very large spill. And your first thing is, I got to go do my bioassay. Well, I spilled it on my arm, and at this point, it's like, I need to go do this bioassay, but then they're like, you can't really do that, because if I do it immediately after my exposure, and in my case I spilt it on my skin, it takes a while for it to absorb through my skin into my bloodstream and get to my thyroid gland. So if I ran right out and did an immediate bioassay, my bioassay would be normal because we haven't given enough time for the iodine to get in. So that's where our 6-hour limit comes from. So if you do have an exposure, we wait a little while, then you come back and you can do a bioassay. If you know you have a spill, we'll probably do multiple bioassays over a very short period of time to see if that starts trending upwards. The other stipulation of this, though, is that it has to be done within 72 hours of exposure. So as I said in my last job, we did iodine so much that basically we did it twice a week. And so basically by doing it twice a week, you very rarely were outside of the 72-hour limit. But if you only do one iodine a week, then basically you would set up your bioassay so that it was performed somewhere in the 72 hours between when you actually made the capsule. And that meets your legal requirement. So again, this is one of those things that it depends on the volume, how many iodine doses you do, things like that. You will set up your bioassay recommendations based on your particular pharmacy. So the important things here are what we consider to be problematic. So the action level set by the NRC, and action level for us is basically, I need to do something. And so if you have somebody that goes through and does a bioassay and we find that they have 0.04 microcuries of iodine in their thyroid gland, you are required to do an investigation with a report that basically identifies what went wrong and how this actually happened. Sometimes it's just operator. They don't know what they're doing. They just learned how to start doing capsules, something like that. But sometimes we find that people are intentionally trying to do something not correctly, or we find that we may have a flaw in one of our pieces of equipment that we're not catching other places. If you reach 0.14 microcuries, that is where we have both an investigation, but we will also send the person for a medical examination, and that medical examination includes looking at thyroid function tests, looking at thyroid uptake, and trying to track over time to see if there's any changes as a result of this iodine exposure. Unfortunately, if you have iodine exposure that's causing any kind of detriment to your thyroid gland, we can't reverse it. And so when you look at these numbers, and you think, well, these are pretty small. To give you some perspective, as I mentioned earlier, sometimes we use I-131 for a diagnostic dose. And diagnostic meaning basically we give you such a small amount that it's probably not going to do much to impact the function of your thyroid gland. So a normal I-131 diagnostic dose is anywhere between 10 and 100 microcuries. So I can easily give a patient 100 microcuries. Let's say 30% of that ends up in your thyroid gland. So 30 microcuries would not be a dose to the thyroid gland or amount of iodine in the thyroid gland that should cause significant decreases or changes in function. And so if you look at these values, they are considerably lower than that. And again, we're going with this whole idea that I would rather catch a problem way early and fix it before it becomes an actual major problem. So for these patients or these people that actually get a recordable bioassay, we obviously have to do some work to figure out what happened, but the chance of you having significant physical effects as a result of that are pretty small. All right, so this is what we're going to do in lab this week. And basically what we're going to do, I'm going to step you through this. We're going to go through and we're going to actually calibrate the single channel analyzer. We want to make sure that our machine is peaked, meaning it is the right voltage so that it actually reads iodine as accurately as it possibly can. This is the kind of stuff, basically what I'm going to do is I'm going to do some of this for you before you get to class, and then we're going to check it and make sure that it actually was done correctly. And that's really the focus of what we're going to talk about. So these next couple slides, it just kind of talks a little bit about what we do, but that will be the very first thing that we're going to do. Really what I'm going to have you do is this fine tuning. So I'll get it to a point where it's pretty close to where it's supposed to be. And then for the first few minutes in class, we're going to be adjusting the high voltage a little bit to try to make sure that, that we really have our machine exactly where we want it to be. And what we'll do is we'll set a window around the typical iodine peak, and we want to make sure that that photo peak for iodine falls within that window. And so again, we'll show you this. I'll step you through this as a group at the very beginning of what we do to make sure that everybody has a machine that's functioning correctly. Once you've got your machine set up to read iodine correctly, then we're going to take a I-131 source, because again, we need to figure out the efficiency of our machine to try to figure out what fraction of the iodine that's coming out of our thyroid gland is actually going to be picked up by the machine. So we need our reference standard at this point. We'll get a reference standard. I will give you one that I will make for you, and it will have a certain amount of activity on a certain date. And so basically you're going to take that source and you're going to count it. Now, statistically, we would like to have at least 10,000 counts, and I guarantee you yours will. And so usually what we'll see with a bioassay, most people will either do 3 1-minute readings and take the average of those to try to get rid of some of the randomness of radioactivity. The other option is to do a 3-minute reading and then divide that by 3 to get counts per minute. My guess is because I haven't made the sources yet, but my guess is your sources will be hot enough that you will not be able to do a very accurate 3-minute reading. Will actually exceed the counting capacity of the detector. So what I'm going to have you do is the 3 1-minute readings and then taking an average. And again, the data sheet I will give you will make this pretty clear. You also want to make sure that you take background. If you are going to take a background, you should be counting the background with the exact same counting standards as you used for the reference count. So if you did 3 1-minute readings for your reference count for your source, you're going to do 3 1-minute readings for your background. Here's the thing that is going to be the most important. So I'm going to give you a little tube that has iodine in it. And basically it will fit into the little hole in the top of the well. When you're actually getting ready to figure the efficiency, you have to stop for a minute and think about how you're going to count your neck. And I'll show you a picture here in a second, which will make a little bit more sense. But unless you can take your thyroid gland out and shove it down into that hole, the placing of the source in the hole is not really going to be a good representation of the geometry that you'll be using when you count your neck. And so you want to calculate your efficiency in the same geometry as how you're going to calculate your neck. And so again, my stellar drawing here, but this is what you're going to do. You're literally just going to lean your neck over the top of the well. And so you're going to see a smaller fraction of the total photons coming out of the thyroid gland. But if we can figure out the efficiency of our machine with that particular geometry, we can always correct what our machine sees back to how much is actually there. So when you get ready to count your source so that you can figure out your efficiency, you want to make sure your source is in the exact same geometry. And you can see I kind of have it laying over the top of the well here. Do not put it in the well because you will get a very weird efficiency if that is the case. So efficiency, again, as I mentioned before, efficiency is the counts that your machine actually saw divided by the disintegrations that were actually in the source that you used. Again, I will give you the information about the source. I will give you how many microcuries that is, and you'll convert microcuries into disintegrations. That becomes your denominator. And then the 1-minute count, or the 3 1-minute counts of your source that are average, that becomes the CPM, what your machine actually saw. And so you will calculate that out. Now, I told you the efficiency of our machine for iodine is usually between 10 and 30%. That's assuming that it's actually in the well. So since you're going to be doing your geometry outside of the well, your neck will be outside of the well, you should expect that your efficiency is probably going to be considerably less than 10%. And that is a completely normal number. And again, when you're doing this, I'll take a look at it, make sure it seems reasonable. So once you've got that piece of information, my machine is 2% efficient. Now it's time to count your thyroid. So we are going to do, again, the same counting setup. So if you counted your source for 3 1-minute counts, you're going to count your neck for 3 1-minute counts. And this is where statistics comes into play, because normally we would like to get to 10,000 counts. I surely hope that you will not have 10,000 counts in your thyroid gland. And so because we can't ever get to that in a reasonable time frame, the longer you can count, the more we're going to start getting rid of some of that statistical variation as a result of the randomness of radioactivity. So basically, you need to count 3 1-minute counts in average. You do have to correct for background. We can just use the background reading that you collected when you actually did the setup of the machine and the calculation of the efficiency. That's perfectly fine because the background radiation will not change that much. So now you have a number of counts. You basically count your gland, and now I know I have X number of counts in my gland. We're going to use that efficiency calculation again. We know the efficiency, you just solve for it. We know how many counts there are, and so by plugging those two numbers in, we can solve for disintegrations. And so once you get that, that number should be considerably bigger than the counts that you're going to get. But that is how we correct for our geometry loss. We'll then take the disintegrations that you got or that you calculated, and using the 2.22 times 10 to the 6 disintegration per minute per microcurie, we're going to convert how many disintegrations were in your thyroid gland to microcuries. And remember our limits, 0.04 microcuries for investigation and 0.14 microcuries for investigation/medical are the limits we're going to be using. And again, hopefully you'll see that your number will be considerably smaller than that. If you do get 0, and most of you probably will, the last thing that I usually have you do, I want you to see how we would calculate this in terms of actually having a value. So usually when we get 0 as the value, I will tell you, okay, I want you to pretend that your counts were 47. And so you could go back and take your counts and actually calculate that into microcuries. So just so you can see the math that's done with this. Now again, math normally done by a computer, so very few people actually hand calculate it, but I do want you to kind of see the process that we go through to actually do this. Again, as I mentioned with this section, this is one of the few places where we focus on statistics. The NRC does require that we have to make sure that the machine we use to do a bioassay test is able to give you results that have an acceptable amount of error. And so when we talk about error, especially in a random substance or random population, we have to use statistics to evaluate that. And so this formula here is what we call the lower limit of detectability. The LLD is specific for each machine, so we're going to have several single channels set up, and not all of them will have the same LLD. But basically that tells you what the lowest number of counts that your machine can obtain and still be considered accurate or acceptable. And so the LLD is simply 3.3 times the square root of 2 times your background divided by time. Now your background is going to be done in counts per minute, so basically time is 1. So you basically take the square root of 2 times your background and multiply that times 3.3 to find out your LLD. Your LLD is going to be in counts. And so that is a useful piece of information, except you can't compare counts in terms of your LLD to, for this particular test, microcuries, because that's what the limits for this particular test are given. So you have to figure out your CPM value and convert that into microcuries so we can compare what the MDA, or the minimal detectable activity for your machine is, and to make sure that the MDA is less than the limit that we are setting for this particular test. So your MDA has to be less than 0.04. If it's not, you can't use this machine to do that particular test. So an MDA is basically, we're just going to use your efficiency again. You've already calculated it for your machine. So you calculate your LLD in counts per minute. Then using the efficiency, you're going to convert that into disintegrations. Then you're going to convert disintegrations per minute into microcuries using the conversion factor 2.22 times 10 to the 6 disintegrations per microcurie. Once you get that number, that is your MDA, your minimal detectable activity. If your MDA for your machine is less than the NRC stated limit, 0.04 microcuries for this test, then your machine is okay to use for this test. Basically what it says is that any number down to your MDA is going to be acceptable in terms of the amount of error. Anything less than the MDA is going to have too much error in it, and so the results are not going to be valid. So if we care about 0.04 for this particular test, we want a machine that hopefully has an MDA significantly less than that, because that means that whatever number we get is going to, even if there was some error in that count, it shouldn't exceed the actual limit. And we'll talk about this a little bit more in class, because this is the one that sometimes people have a hard time getting their head around. But basically, if your MDA, when you solve for MDA, if it's greater than 0.04 for this particular test, you can't use that piece of equipment. There's just too much error in that reading, and what you're getting is not going to be accurate enough to make a good representation of how much iodine is in your gland. All right, so to close this for lab next week, you are each going to be doing a bioassay on your own thyroid. As I mentioned, we will set up the machine, which basically means we're going to check the calibration, make sure it's calibrated for I-131. I will start this process. I'll get it kind of close, and then we will go through and we will double check it. So basically what you will be doing is just fine-tuning the setup to make sure that it truly is calibrated for I-131. Then we'll determine the machine's efficiency. Then you're going to count your thyroid. And there are probably going to be 2 of you at each piece of equipment. So you're going to set it up together, and then basically you will each individually calculate your own thyroid bioassay. And basically once you've counted your thyroid, you'll go through this whole process and determine the microcurie amounts of I-131 in your gland. And I will give you a sheet for this, so it'll make a little bit more sense when you're collecting your data. But I'm assuming that since most of you do not handle radioactive iodine in any way, shape, or form, that your number should be 0. Basically, you will probably get a count in your thyroid gland that's less than background, and that's okay. So as I mentioned, I want you to see what happens when you actually do get a number. And so after you get through that point, I'm going to tell you, I need you to pretend like you had X number of counts in your gland, and I want you to go backwards through the process. So you're going to say, I have this much microcuries of iodine in my gland, and then you're going to go back and try to figure out how many microcuries that actually amounts to, and then compare it to a limit. I think you'll be surprised, even though the numbers, sometimes you think, oh my gosh, that's such a big number. Remember, your single channel analyzer reads each individual photon interaction. So a big number, 500 counts, is still only 500 atoms that gave up their disintegration. And so that's really, in the big picture of how much activity or how many disintegrations happen in a microcurie, millicurie, curie, that's still a fairly small number, but we'll let you practice it just to kind of see. Now, to make things go a little smoother, I'm actually going to divide each lab section in half. So half of you will come for the first hour, half will come for the second hour. That way we don't have to worry. I mean, this process shouldn't probably take much more than a half an hour, 45 minutes tops when you actually go through this process. And so instead of trying to have multiple people on a single machine, if I divide you up, then you can have groups of 2, and we'll have plenty of machines so that everybody will be able to go through and do their own thing. I haven't done it yet, but I will probably this weekend, I hope. But I will basically go through, and in this particular lab, I will have a who comes when type of posting. And so I will have it divided, how many people are coming at 9:30, how many people should come at 10:30, how many should come at 11:30, and how many should come at 12:30. Basically, once you've counted your gland, you do all your calculations, including some of the statistical calculations, you will be done with lab, and then you can leave. So this lab is really more instrumentation based, but it is the clinical application that really for us is important to consider. And as I mentioned, this is one of those topics that people think, especially regulatory people, think are very important. When I worked in Chicago, our state regulatory agency basically just said, we're coming in one day and we're going to take a pharmacist into the conference room and we're just going to ask them questions about bioassay and air monitoring. And most of us were like, we just do it. We don't know how it's done. We don't know why it's done. And so I think it's good that you kind of get a picture of why we do these things in the pharmacy. And again, all of them tied back to trying to keep your radiation exposure as low as possible. So that'll be lab for next week. The week after, we'll go back to doing technetium again, which will be a little bit more convenient. It's just much more convenient to do this week because I'm going to be gone up to class. So I know this doesn't necessarily fit really well in the whole scheme of what we're doing, but it's something that you need to make sure that we cover before the end of the semester. So hopefully that is clear enough for you. Like I said, we'll be doing most of this as a group, so I don't think you're going to find this is going to be too terribly challenging. You have nothing that you need to do to prepare for lab. You'll just come in, I will hand you the sheet. The one thing though is that since I do have to talk a little bit, and it's easier to do this as a group, we will not start until everybody shows up. So obviously if you can get there on time, that would be helpful. So I will see you then on Wednesday, and hope you all have a nice weekend.